Hello everybody, good afternoon. We will start the session soon. Just confirm if you can hear me.
Yeah, we can.
Can you type yes on the chat box if you can hear me? Yeah, hello Sunil sir, good afternoon.
Good afternoon.
Yeah. Hello guys, good afternoon to everybody. So today I welcome everyone to this session 21. So conducting this open session, we have started some quite a long time back now, and because of your participations and your interest, we have come towards the open session 21 today. And today we will be discussing about one of the very important topic and requested by a lot of people, and I think it is you will be able to gain a lot of knowledge about this topic today. So the topic is industrial PLC design using software configurable IOs. So this presentation will be done by the team from Analog Devices. I hope most of you know Analog Devices. And I have, as a panelist along with me, I have Mr. Sunil and Mr. Anup from Analog Devices. And along with the Analog Devices, I have Mr. Vasudev, Director of PHYTEC Embedded Private Limited, Bangalore. So without further delay, let me give the stage to Mr. Sunil to continue the presentation. And as usual, you can, if you have any questions during the session, you can type on the chat box. And if you have, if you are facing any issues during the session, you can let me know, or you can disconnect and connect it back. And also for the participant who's joined in YouTube, so you can write your questions on the chat box available on the live chat. Okay. So I welcome everyone again, and I give the stage to Mr. Sunil.
Thank you, Mr. Dev. Am I audible?
Yes, sir. You are audible. Sir.
Okay. Good morning. Good afternoon, everyone. At the outset, I thank PHYTEC, especially Mr. Vasu and Mr. Dev, for giving us this opportunity. I can see around 18 people here. So the session for the day would be done between me and Anup, my colleague, who is dialing in from outside of Bangalore. Before I get in, let me just try sharing my slide deck so that there is no confusion. Hold on. Just let me know when the slide deck comes up.
Yes, we can see your slide. Mr. Sunil, just to correct, actually, like I am Ashraful, like I am using RB Dev as a account basically. Okay. So my name is Ashraful.
Sure. Okay.
Yeah.
Okay. So let me just kick off. So quick introduction. My name is Sunil. I've been with ADI for more than 20 years. I have been involved in the distribution side of the business for more than 10 years. And of late, I'm working as a corporate account manager. The primary role being to work with distribution customers to work out the long-term strategy and growth. Along with me is my colleague Anup. I will let him introduce himself, but a very quick word of introduction. He takes care of the industrial application support for all our customers in India, both direct and supported through channel. And he has been involved in supporting many of our global accounts like Honeywell, Emerson, ABB, Siemens, and similar companies, and brings with him a lot of expertise on the industrial domain. So the topic of today's discussion, based on discussion we had with PHYTEC management, picked up something which is close to our heart for ADI as a company, and is something we have been aggressively trying to push into the market, and all the inputs and feedback from you as customers would be great to kind of further share knowledge and information to see how it can add value to your products and offerings. And if it also means bringing in PHYTEC as a company to be involved as a design partner to enable any of your designs, we will be happy to discuss that as well, right? So is my slide moving?
Yes, sir. Your slide is moving. Can you make it fully screen?
Okay, just hold on.
Yeah.
Is that better?
Not yet. Make it full screen.
Okay, I think I will have to share that again. Just hold on.
Okay. No, sir,
is this better?
Still the same. Yes. Now it is full screen. Correct.
Okay. So I'm going to spend a few minutes initially giving the basic context of this product portfolio and the value proposition, and then later Anup will do a deeper dive into the product solutions and the value proposition. So some of you may be familiar to Analog Devices as a company. I think more than 50% of our revenue actually comes from industrial market, and industrial automation happens to be the biggest focus within that segment where we continue to invest. If you see, today's topic, I would like to focus our discussion on the trends in the industrial market, especially on industrial automation for markets like PLC and DCS, and especially this evolution to the Industry 4.0, right? And if you see some of the pictures out there, these are areas where ADI has been traditionally very successful and heavily invested. Things like motion control, robotics, Ethernet, in terms of the connectivity and the network architecture for many of these factory automation applications. Condition-based monitoring, which again, we will probably touch upon a little later. And then across all these applications, what is a common theme when we talk about Industry 4.0 and scalability and connectivity is about functional safety, not just as a system, but also at a component level, and then the security layer. So across all these verticals, ADI has been investing, and we have just listed some of the key technologies which are very important from this standpoint. Number one, I talked about scalable Ethernet architecture, right? So here what happens is, while we have multi-protocol switching technologies out there, especially for these time-critical applications, it becomes very significant to have this timestamp. So this is an area which ADI has been heavily investing in terms of real-time deterministic Ethernet switching technology. This is not a topic of discussion, but for the sake of completeness, I'm just trying to highlight where ADI is investing. Software configurable I/O is the topic we will talk about. We will get into detail. So I'll just keep that aside for a moment. And then condition-based monitoring. So here, it's not just smart sensing in terms of MEMS technology. It is also about connectivity to the cloud and how intelligent is your software and algorithm to do a predictive analysis. So this is what we have been seeing as the evolution when we go jointly on this path to Industry 4.0. Maybe India is a little behind in terms of the curve as compared to some of the advanced markets like, let's say, even in Asia, between Taiwan and Korea. But we do see clear indications that all our customers would eventually reach there because there is no other choice but to do it in terms of their own survival. So what is ADI doing on Industry 4.0? If you look at the typical diagram, right, on a typical industrial environment, you have all these field instruments, robotics, condition-based monitoring in a shop floor, or maybe a wireless mesh technology connecting, or a wire technology like industrial Ethernet. And on the right, you would see some of these verticals within the Industry 4.0, which is evolving. Software configurable I/O, which we'll just talk about. We are seeing more and more of intelligence coming to the edge at the node. So it is processing at the node and the processed information being fed back to avoid too much of data getting into the network, into the cloud for further analytics. And then I talked about some of the technologies on the deterministic Ethernet, which helps to avoid a lot of chaos out there when we talk about acquisition and back to the cloud. The condition-based monitoring, which is about predictive maintenance, so that we get to know ahead of time whether a particular pump or a motor or a compressor is going to fail, and make sure that downtime is avoided, thereby saving a lot of time and dollars to the company. And if you look at the fundamental theme across these technologies, especially when we talk about software configurable I/O, it's all about bringing multiple levels of flexibility, efficiency, safety, which cannot be compromised at any cost, and also security and rugged, robust communication, right? So now we will get into a one level below, deeper dive into what ADI means by software configurable I/O. So on the right, we just highlighted some of the value proposition which Industry 4.0 is going to bring in. And as I said before, it's all about sensors out there in the field, intelligent sensors, connectivity, and then efficient analytics, safety. But I just highlighted few of the specific value proposition which is going to be of interest when we talk about software configurable I/O. One is interoperability. And then when companies try to invest, they need to make sure that when technology evolves, whatever they invested doesn't become obsolete. So it's all about future proofing. And then every time they introduce a new system or a product into the network, they should not have this hassle of recertifying that product or equipment. So it's all about flexibility, modularization, so that it eventually saves not just development costs, but also the deployment and cost of configuration when it's deployed on the factory floor, right? So I'm just spending a couple of minutes to look at how this has been evolving over time. Traditionally, we have seen that many of these, if you see the typical hierarchy in the factory automation side, you have these 4 to 20 milliampere loops, which has been prevalent. And ADI has been a significant player when we talk about the signal acquisition, processing, and control into all these sensors and actuators out there in the field. And then you have a typical junction box, which communicates within these systems through 4 to 20 milliampere. I'm not saying it's good or bad. Each of the technology has its own pros and cons, and we have just tried to highlight it. We're not going to get into the detail, but I just wanted you to be aware that this had its benefits and certain disadvantages. And then people moved on as far as the connectivity is concerned into different field bus technologies. So here again, it comes with its own benefits and disadvantages. I think the data speeds went up, but then there was a challenge about multiple standards out there, and there was no interoperability. And then there was a cost angle and need for trained people to be available. So this came in to solve certain problems, but it also brought in certain other problems to be resolved. And today, as we speak, many of these advanced factory automation technologies, at least on the connectivity side within Ethernet, is moving to something called 10BASE-T1L, which is a technology which ADI has been proactively investing and participating in the industry standard forums to evolve. And we have the 5s which are released, but this is not a topic of discussion. But I just wanted you to know that in this evolution, the connectivity is moving from 4 to 20 milliampere loops as legacy systems to different Ethernet field bus technologies to 10BASE-T1L, which is what is very prominent today. And we will see how all these coexist in a network. So what is software configurable I/O? If you see the bottom right, it talks about key technologies, what ADI brings in, right? I mean, we had different sensors. Signal conditioning has been our core competence, be it op-amps, converters, A2Ds and D2As, and then all the digital I/O interface technology. Isolation has been a big area where we have shipped billions of channels with zero rejection worldwide. And then we acquired this company called Linear Technology 3 years back, which brought in the power franchise. So leveraging these technologies, we have tried to bring in this configurability into this I/O systems. So what I mean by configurability, which you will get to know in a better depth a little later, is about if you look at a component level, any pin able to do any function with configurability on the fly. So this kind of de-risks your impact in terms of commissioning. And let us say you commissioned a system, tomorrow you want to change the architecture because your mix of equipment is changing, you can just configure through software on the fly, but the basic hardware remains the same. So this addresses all the problems and what we were talking about in Industry 4.0 when different systems coexist. And it also brings in also a layer of security and robustness into the network by leveraging these technologies. Now, Anu will talk in detail about this, but at a very fundamental level, what it means is if you look at the number of channels in a typical PLC system, you would have inputs coming in, which could be analog. You could have outputs going in, which is analog. You could have digital inputs or digital outputs. So we are talking about a system where inputs can be configured through software, outputs can be configured through software. So these are typically leveraging our strength on converter like ADCs or DACs and bringing in that programmability aspect. And also on the I/O lines, which is sitting between the field and the control center out there, bringing in the option to configure through software the I/O lines to be any of these to cater to different inputs. And please bear with me till Anup gets into the more detail about what this all means in terms of components and hardware. Now, if you look at putting together whatever I said so far, SWIO is aiding this transition of this Industry 4.0 from a legacy system to an Ethernet-based T1L architecture. So if you see here, you have all these systems coexisting, the 4 to 20 milliampere loops, traditional, I would say, actuators. You have all these brownfield Ethernet devices, meaning people lease out equipment from third parties and they bring in newer technologies, and they have to connect to the more modern PLC and DC system, which are at the higher end of the architecture. So we bring in this, what we call a remote I/O, and this concept of software configurable I/O to help bridge the gap between these legacy systems and most modern PLC and DC systems. So at a granular level, each channel can be configured for whatever you need on the fly. You can have any different combination, and it is granular at a channel level. So you don't need to bring in redundancy in terms of multiple I/O cards because you need to take care of future capacity enhancement. The existing system can be reconfigured to take care of that. And then what happens is, from an installation standpoint, you don't need to know how your system would evolve over time, and you're kind of preempting that capital investment to be reused for different architectures in future. So I was talking about the real world out there having either analog or inputs or digital inputs and outputs. We are talking about a chip or a combination of chips which can be configured to meet all these parameters. And when we map it to different end products, right? I mean, you have low-end PLC systems, you have maybe a mid-end and a high-end PLC, depending on the complexity of the system and the channel count and the accuracy. We are talking about a combination of input devices, basically, precision ADCs, precision DACs with very high level of integration to bring in that software configurability on the input side. Likewise, on the output side, precision DACs with, again, a configurability to give either current or voltage output, which can be configured through software, or just I/O systems which bridge the legacy to the modern T1L systems with that configurable I/O, which are, again, a mix of products with a different channel count, which can be configured through software. Many of these products are released and in production. Some of these are in concept, and I've removed certain devices which are in the roadmap, which are shared under NDA. And then I will let Anup.
We are unable to see the screen, please.
You cannot see the screen now?
It's visible to all.
It's visible. It's visible, sir.
It's visible to all.
Nagesh, sir, if it is not visible, you can disconnect and reconnect back. It's visible to others.
Okay. So now at this stage, I want to bring in my colleague Anup to take you through a deeper dive of what a typical PLC architecture would look like and how SWIO fits into this in terms of configurability and evolution to Industry 4.0. Anup, are you there?
Yeah, thanks, Sunil. Am I audible?
Yeah.
Yeah, I shall share my screen.
Okay, let me just take off my screen so that you can read your screen. Hold on. Yep.
Can you guys see my desktop?
Not yet, but
No, not yet.
yeah. Can you make it full screen?
Yes, no.
Is it okay now?
Yes, it is okay. You can continue, sir.
Yes, thanks. Thanks, everyone. My name is Anup, and I work as a field application engineer at Analog Devices. And I primarily take care of the industrial automation and process controller segment within the company. So Sunil has given a very good understanding of where we are moving, how we are planning to address the new generation of industrial automation systems. So as he mentioned, PLC is an inevitable part of any industrial automation. So if you look at the below architecture, give me a second. Below architecture, PLC is basically a digital computer which has got input as well as outputs to control a particular process or a manufacturing automation. When we talk of inputs, basically the PLC need to accept industrial inputs like voltages, which ranges from 0 to 10 volt or plus or minus 10 volt, and currents in the range of 4 to 20 milliamp or 0 to 20 milliamp. Additionally, they also have to deal with temperature sensors like RTD, TC, then pressure sensors and resistance. These are the typical industrial sensors. Those get connected to the input module side of a PLC to control a particular process. Once you have these inputs, there is a processing which might use a small microcontroller, or it could be a very high-end embedded processor, depending upon the application, generates outputs in the form of voltage and current to control a particular output device. So those output devices could be a solenoid or a position valve or something like that. So basically, the PLC accept process variables and do some manipulation on that and generates output to control the system in equilibrium. And locally, there is a power supply to generate all power rails required for the components within the PLC system. And the input and output may call for isolation based on the system requirement. And in general, these PLC systems are connected to another PLC system or SCADA system through communication protocols like Modbus, CAN, Profibus, Ethernet, and other way of communication. So if you look at this architecture, it's a bit complicated. In case of an input module, we can think there could be an ADC to accept these inputs. But look at the complexity. To accept a voltage or current, you might need just a resistor and an ADC to sense it. But in case of a temperature sensor like RTD or TC, that is not sufficient. You may need a precision current source with an ADC. So each of these input do call for a fixed set of hardware inventory to handle with those inputs. A similar case with the output module as well. To generate voltage and current based on the computation happens within the processing unit, you need a fixed set of hardware and software to deal with it, which is quite complicated, isn't it? You have about 5 to 10 type of variables, and you need to have different hardware inventory to address each of this module, which is complicated. You will have to maintain that inventory, and when you look at the maintenance engineer who is out there in the field, need to be well versed and trained sufficient enough to deal with all these hardwares to resolve issues. So So we thought of investing in this particular area to ease your development cycle, in addition to giving you a highly precise and reliable solutions and with high performance. That is the concept of software configurable I/O. So wherein what we do is we basically give you a black box with which you can configure through your software for any of your input output functions. So what is software configurable I/O? As far as the user is concerned or a developer is concerned, you really don't have to worry about what is built into the chipset. It could be ADC, it could be a DAC, or it could be a threshold comparing circuitry, but you really don't have to worry. It is just a black box for you. You communicate to the black box over SPI or I2C and configure it the way you want. Today you might configure it for a input voltage sensing. Tomorrow the same channel you may reconfigure it for an output voltage or an RTD or a TC. It's that simple. So just communicate and tell the IC or the chipset that I want a output module or an input module with the proper settings. It just get configured. So you get any function at any pin, however you want, as the system demands. So what is the final objective here? So you get ultimate flexibility and configurability, which is the trademark of Industry 4.0 to bring in efficient production systems in place. So what value it brings into the system once you go for industrial software configurable IOs? What are the advantages that you have? As I mentioned earlier, as against the legacy fixed hardware designs for your various inputs, it all converted into a single chip. So your inventory has come down and you do not have to deal with many of these modules separately. And what happens is when you look at the testing point of view or development point of view, you really don't have to deal with 4 different sets of hardware and its testing and its certification. Rather, you deal with a single chipset. You do the development, you do the testing and get it certified. Afterwards, it's just an implementation. So what you look today, something like this, wherein you have a HMI, power supply and various modules sitting like RTD, TC, digital output, analog output, all those things, it all just get replaced with the software defined IO modules. And based on the application and based on the requirement, you just configure them as the system demands. And it is that flexible when you look at the SWIO concept. You really don't have to think too much on your system design. Now, look at the pie chart here. When you look at a plant implementation, like an oil refinery or a manufacturing plant, the hardware cost is only 20%, but you spend significant amount of money on your system design, which is about 25%. Installation is about 25%. Commissioning some 20%. Training the field engineers, which is 10%. So altogether, this is about 80%. When you go for a concept like software defined IO, you actually reduce the complexity in system design, as I said, because you will never know how many IO points you need in a particular area or particular rack or particular point, and how those things will change tomorrow, because tomorrow there could be an addition of temperature sensor. Then how will you deal with? Either you'll have to buy a new IO module, add it to the existing system, which is like additional commissioning with additional training, and you'll have to really spend time on that. So that way, when you go for SWIO concept, you bring down the system level system design complexity. Similarly, the installation by reducing the manpower. And when it comes to the training of the maintenance engineer, you really don't have to spend too much time on it, because he is going to basically deal with just single hardware and how to configure it. That way the maintenance engineer become very well versed with the hardware and he makes minimal errors in the field. And when it comes to the commissioning, with SWO points in place, you really don't have to add points as and when it's required. Based on the future requirement, you can have some points already in place when the commissioning happens, and in the future you just configure it for whichever inputs you want. So basically, SWO concept bring in high level of operational efficiency. Henceforth, you save cost when you go for this kind of concept, and this holds good for factory automation, process control, all those segments. And this is one particular case wherein SWO can show its value. This is just one use case I am explaining here. When you go for a building automation technology, you will have to deal with a number of sensors like humidity sensor, temperature sensor, gas sensors, and there could be valves operating for the safety and other mechanisms. And you will never know how many sensors you need in a room or in a building, because today you might have only one humidity sensor or one temperature sensor. Tomorrow you might or the customer might ask you to increase one more sensor. It could be a humidity sensor or it could be an ambient light sensing sensor. How do you deal with? If you had looked at the traditional way of design, you will have a fixed configuration, and when such requirements comes in, you will have to add additional IO points. You'll have to configure them. Then you'll have to train the maintenance engineer. So a lot of work happens in the commissioning side, which is very difficult and time consuming, and it can make human errors as well. Instead, you go for a concept like SWO, wherein you will have these SWO points locally sitting inside a particular room or a particular building, which has scalable IOs. During the installation time itself, you may decide to have 5 or 6 IO points more. And tomorrow, when some sensors coming in over the software, you'll just configure it for an input module or an output module, or it's a digital input. It's as simple as that. So going with a concept like SWIO brings a single platform for any control design in a building automation. And obviously, it reduces the inventory and BOM cost. And you will have increased reliability because you are dealing with a single hardware, and the testing and certification is done on a single hardware, and you have multiple points of that. In addition, in case if you want redundancy, which is also easy to bring in such kind of designs. And this SWIO technology comes with a lot of inbuilt diagnostics. So that would be good warning and alarm when you look at a concept like remote IO points. So I hope you get an idea here, the advantage of SWIO technology in a building automation scheme. Move to a concept like SWIO in the automation side, you have reduced R&D costs. Basically, you are dealing with a single hardware and its associated software. And the software could be different modules, but the hardware remains the same. Since it's just a simple single hardware, you have a faster development time and a product launch. Additionally, you will have a lot of flexibility for the future. As I mentioned in the building automation case, you can configure, reconfigure, you can have better scalability as and when the system demands. So it meets your present and future needs in an elegant way. And you do not need a lot of resources, especially in the maintenance engineering side. The engineer need to go through a single hardware. He just need to get well versed with it, and that way he will be able to manage and resolve issues at a faster rate. Now that we have gone through the concept of PLC and the SWIO and how is it useful for the system, I would like to introduce a few products from analog devices which really meant for these kind of applications. The first part is AD4110. It's a software configurable universal analog front end. There could be applications wherein you may need an input module in the PLC, which need to measure a voltage input, or it could be a current input, or it could be a temperature input like thermocouple or RTD. Traditionally, when you look at the design, you have to have a different hardware, as I mentioned earlier, and a different software. We are giving you this particular chip, which is AD4110, which has all necessary mechanisms built into the chip, and that can be configured over SPI for any of these inputs. That way, you will have a single hardware addressing all your inputs, industrial input. Henceforth, it's a universal AFE handling all industrial inputs. Now let us look some of the features of this particular part. This part can be configured for current inputs up to plus or minus 20 milliamps, voltages going all the way up to plus or minus 10 volt, and it can be configured for thermocouple. And in case of a RTD, the part can be configured for 2-wire, 3-wire, and 4-wire RTD. So this implies it's a complete universal AFE for all type of industrial inputs. And the part is developed on a high voltage process. Because of this process, each of the input pins are protected up to plus or minus 30 volt. It has a definite advantage because when you go for EMI, EMC testing, especially the ESD surge and other testing, you will have the ESD diodes on each of these pins. What can happen if you imagine we had given only a 5 volt or 10 volt protection on each of these pins, maybe 15 volt, because the part is capable of accepting up to 10 volt. Then you have to choose a ESD diode with a lower voltage. The moment you go for a lower voltage, in case of a ESD diode, your leakage current increases, which decreases or reduces your accuracy of measurements. So with the high voltage protection built into the chip, you have a high level of flexibility in selecting protection components in terms of its threshold, in terms of its leakage current specifications. And this part has got internal current sense resistor as well. When you think of 4 to 20 milliamp, before feeding to the AFE, you in traditional way, you will have to drop it across a resistor and measure that voltage, then convert back it into the current. Those resistors are inbuilt to the chip so that you do not have to have these resistors outside, which used to be costlier. Usually we need resistors with 0.1% accuracy. And you can imagine if you have 5 or 6 or 10 channels of IO points, then you have to procure 5 of them, which can increase the system cost significantly. We have used precision resistors inside the chipset to address and ease in your system design. And the part offers a very good throughput rate. It go all the way up to 60 kSPS with a noise-free bits of 16. And at 50-60 samples per second, you get 20 noise-free bits, which is very, very good in case of industrial designs. And the part is offered in a temperature range of minus 40 degrees C to plus 105 degrees C. This is the architecture of the part. Basically, the architecture can be brought into 2 sections. This is the front end AFE section, which deals with all high voltage signals. It has a high voltage PGA, fine-tuned for high level of accuracy. And there is switch mechanisms, very versatile switch mechanisms, excitation sources, and biasing sources to deal with different set of sensors. And you also have the sense resistor built into the chipset for the current measurement. Once you feed some signal, you will configure this portion accordingly through the software to accept and handle and manipulate those signals. Once the second part of the chip is a high performance 24-bit ADC over here with a very good and flexible digital filtering. The digital filter offers you noise-free bits up to 20 at the highest data rate. and you have different options like sync 2, sync 3, sync 1 plus sync 5, all those here. And it do also come with the internal reference to meet all your accuracy levels. I would specify, I will come back to those specs again. What accuracies are we meeting with the internal reference? So this is all you need when you use 4110 for a universal analog input module. You just need a couple of passes around it to deal with. And with this simple resistor and capacitor combination, we are able to pass all EMI EMC tests in terms of ESD, surge, and EFT. So that was a module which was primarily dealing with all of your industrial inputs with software configurability. There could be a situation, especially in the automation side, factory automation side, you will have only 4 to 20 milliamps inputs or plus or minus 10 volt coming into picture. You may not have any other sensors coming over there. In such kind of applications, we are giving you this particular part, which is AD4111 or 4112, which can be configured for either voltage or current input. So basically, this is a software configurable voltage and current input module. So, so this part basically meets all your system requirements with the highest level of integration. So since we integrate a lot into the chip, when you look at the system level design, it helps you to reduce the cost, and it reduces the PCB size, and there is a inbuilt calibration features built into the chipset, which will further reduce your software overhead. So this is a basic block diagram of the chipset, AD4111 or 4112. This has built-in sense resistors. You can see here. So these sense resistors are used to measure the current inputs, whereas these precision high voltage dividers are used to measure voltage inputs. The part works on a single supply, 0 to 5 volt, and it's capable of accepting 8 voltage inputs going all the way up to plus or minus 10 volt, and 4 current inputs with built-in resistors, sense resistors, going all the way up to 0 to 25 milliamps. Let us look at some of the accuracy and other features built into this particular chipset. So first thing is we use a 24-bit ADC here, and it can give you up to 6.2 kilosamples per channel, and it gives 16 bits of resolution at 1K SPS per channel, which is quite good in automation applications. And you see the 50 and 60 hertz simultaneous rejection figure. It's about 90 dB. So 90 dB typical is a very good figure when you look at 50 hertz, 50 and 60 hertz rejection. And the part offers a input impedance greater than 1 mega ohm, and the accuracy of all your measurement without calibration is 0.1% over full scale. This is really good because there are some applications wherein you can have accuracy levels going all the way up to 0.2 or 0.25. In such applications, you do not have to do the calibration, because the linearity and the accuracy of the part is really good. And when it comes to the current inputs, it offers 0.2% accuracy at 25 degrees C, and this is also really a good feature of the part, and reduces your overhead on system calibration. Now we have seen the parts that addresses the input modules. One was a universal analog input module, and another one was a voltage and current input module specifically for the factory automation side. Now we will look at the output side, where you can configure the output between voltage and current using your software. So here I am going to talk about a part which is AD5758 or 5753. This is a special bipolar precision DAC, wherein you have the output, a single output that can be configured for either voltage or current. When I say voltage, the voltage range could be plus or minus 10, 0 to 10, or 0 to 5, or plus or minus 5. And in the case of current, it could be 0 to 20 milliamps, 4 to 20 milliamps, or 0 to 25 milliamps. The part comes with a 16-bit monotonic DAC with the inbuilt reference, and the accuracies of 0.05 of TUV we are 0.1 percentage of TUV we are able to meet without calibration. And the part also features a special feature called dynamic power control. What it does is, assume you are setting the output here for 4 to 20 milliamp, and you imagine a sense resistor of a 250 ohm connected over here. So when the 20 milliamps goes through this way and across the resistor, you develop a voltage of 5 volt, right? But what happens in the chip? This chip usually get powered in the industrial application 24 volt. So 24 volt into 4 milliamps. So much of power is dissipated over the chip. What is the disadvantage of that? You won't be able to increase your output channel density, because increased power means increased thermals, and increased thermal means more and more drift parameters are associated with your design. So you will have to limit your number of output channels if you're not having good power schemes in place. With DPC, what will we do? When you have here 20 milliamps multiplied by 250 ohm, which is 5 volt, we maintain a voltage here through this mechanism, which is just enough to meet that complaint. Say probably, for example, we maintain it at 8 or 9 volt or 10 volt. So the dissipation over the chip is now has come down to 10 volt into 20 milliamps, which is significant, and which is very, very significant when you have multiple channels to deal with. That is the point I have made over here. With DPC, you can have more number of channels compared to any other solution present today in the market, which saves area as well as the cost. And the part is developed on a 60 volt process, which brings in very, very good ruggedness and robustness in operation. And as I mentioned earlier, in case of 4T111, this would ease in your protection schemes with the choice of ESD diodes and surge suppressor, etc., etc. Now, I would like to introduce another part, ADP 1031. This is basically a power supply part, and it is used primarily along with the AD5758. As I mentioned, based on the system requirements, you may the system may call for an isolation between your processing unit and the output unit, because output unit is your field side portion, and the MCU is the controller side portion. Due to safety reasons, there are isolation requirements in some of the applications. So wherein this part becomes very handy with AD5758. So this part basically works as a flyback controller with a high voltage MOSFET built into it, and the voltage it can handle is about 125 volt, and it generates 3 isolated supply, one positive rail, one negative rail, and one buck rail, and it has inbuilt SPI isolation, so that you can communicate to your DAC through this SPI. So with a single chip, you are getting power supply and data isolation. So this figure basically gives you a better understanding on that particular concept, wherein you need channel-to-channel isolation or output module isolation. So 1031 helps to generate these 3 supplies for AD5758. And the 5758 talks to your controller through the inbuilt data isolation. So with just 2 chipset, you are meeting your isolation requirement, and the design becomes very sleek and very minimum, and it reduces the PCB area as well as the number of components when you look at a traditional way of design. Now we looked at 3 types of products. One was addressing the universal input, second was on the voltage and current input, and third one was on the output module. Now we will get into a true SWIO product wherein you can configure a single chip for both your input or output configurations. So the part is 74413. The part is primarily targeted for process control, industrial automation, and building automation controls. It's a 4-channel part, and each channel can be configured for any of the industrial input output. Those inputs could be a voltage input or a current input, or the pin can be configured for voltage output or current output, and additionally it can be configured for digital input and RTD measurements. And it is hard compatible, and the part has got a lot of built-in diagnostics to identify sensor open, sensor short, or the SPI connection lost, the loss of SPI connection, etc. And here basically when you wanted to look at the design without this SWIO product, you may have to use fixed function IOs for your analog input, analog output, and discrete inputs. But with the 74413 coming into picture, you have a single chipset to deal with. You configure this 74413 based on your system requirement for analog input, analog output, or discrete input configurations. And we use a 16-bit ADC and a 13-bit DAC inside the chip with the built-in voltage reference to handle all these functions. And with 74413, what basically we are going to have, we are going to have a single platform design which is highly flexible for your present and future needs, because you can configure it for today's need, and you can reconfigure it for tomorrow's need as well. And it reduces inventory quite a lot. You can see from this picture as well. If you have to have all these functions in a discrete way, you have such a big inventory which is brought down to a single chipset. And some of the specifications of 74413 we will have a look at here. So in case when you configure the 74413 for analog output, analog output, that means you can configure it for current output or voltage output. And in case of current output, you get a total unadjusted error of 0.28 without calibration. And in case of voltage output, it's about 0.2%. Without calibration, such a total unadjusted error is really good. And if you do the calibration with offset, gain, and other thing, this can be brought down to 0.2 or less than 0.2. And in case of inputs, it offers 0.1% accuracy for the voltage input, and 0.17 for the bipolar input, and for the current inputs it's about 0.1%. These figures are without calibration, please note that. And the digital input scheme is compatible with IEC 61131-2, and it addresses all types 1, 2, and 3. And it's a very robust architecture, robust architecture with high voltage process. The inputs pins, not only inputs, all pins are protected up to plus or minus 40 volt, which makes your external protection component selection very easy, as I mentioned in the previous cases. So this is the portfolio that we discussed so far. When you want to have a analog universal analog input module, just consider 4110. If you want to have a current and voltage input module, you can go for with 4111 or 4112 or 4115. And in case of a configurable output, you can consider 5758. And if you need isolation, then consider the companion part ADP 1031 along with it. And for a software configurable input output system, that means a single IC, if you want to configure for input as well as output applications, something like a building automation control, you can consider 74413. which is a truly software configurable I/O. Now that we have looked at the concept of SWIO, PLC architecture, and some of the products that we have released for this particular segment, we will look at the PLC architecture, how simple, sleek, and elegant with these offerings. Definitely, you need a embedded processing unit when you design a PLC. It could be a SOM or a controller of your choice. When you want to go for a universal analog front end, just consider 4110, which is capable of accepting all your industrial input and bring isolation with some of our galvanic isolators if system demands. Now there are applications where you want to deal with only voltage and current inputs with the unipolar supply. You just consider 4111. And if you need a configurable output, go for 5758. And use 1031 if you want to have isolation between your controller and the output module. And if you want to address Industry 4.0, wherein your system requirements changes dynamically in terms of I/O pins, go for 74413, which is a code channel part, and it's a pin. I won't say input or output. It's a pin can be configured for input or output as the system demands. So you can see from this diagram how efficient you are going to be with the solutions that Analog Devices is going to offer. If you want to design a PLC which is highly versatile, configurable, and flexible in nature, addressing the high demand in the industry's IoT 4.0, only Analog Devices products can offer such kind of flexibility and configurability as on today. With this, I end my presentation. I hope I could give you a good understanding of SWIO family products and how is that going to help in a system design and the plant implementation in terms of operational efficiency and the cost and inventory. Thank you.
So, Mr. Ashraf, I think we're done with the slide deck.
So thank you, Mr. Sunil and Mr. Anup, for your presentation. It was very really informative, and it was I hope the participant has got a lot of information today about Analog Devices, their offerings, and their future plannings for the products and services. So so we have some questions on the chat box. I can see we will go through one of some of the questions, and also we are about 1 o'clock right now. So I request all the participants, if you have questions, quickly jot down on the chat box so that we can complete the things faster. And I can see most of the questions even Mr. Sunil has tried to answer. So let me take some of the questions. Let me just scroll down on the chat.
So maybe Ashraf, I think one of the questions which I didn't want to put in so many words was about the analog versus digital isolation. So Anup, if you can see the chat box, right? There was one question about the approach between analog and digital isolation. You want to take that quickly?
Yes. So when we compare the analog and digital isolation, it has analog isolation is a traditional way of isolating the input signals. Usually we use linear optocouplers for this particular application. So the disadvantage or the concern with that is when you use a optocoupler for this kind of application, first thing is it's a power consuming. Second thing is that the linearity degrades over time because of the CTR ratio. And that brings in a lot of disadvantage when it's a closed loop system, or rather in the high accurate systems. So the idea is to avoid this kind of non-linearity and bulkiness when you wanted to isolate the signal. Rather considering isolating the signal point of view, we bring in a digital isolation. When I say digital isolation, the isolation comes after the ADC. So you will have a ADC or DAC which is communicating over I2C or SPI. So there you are not losing any linearity because you have not introduced any components in the front end which play with your linearity like optocoupler. Your ADC samples the signal right away at the connector or the point of contact. Then it passes it over through SPI, through an isolation barrier. There you have nothing to lose. You already have the 16-bit information there, and the accuracy totally depend upon your ADCs or DACs accuracy and resolution. And and, uh, and additionally, the cost incurred here is much lower than the analog isolation technique. You can see a good analog isolation technique cost you something not less than $2 to $3, whereas a digital isolation will get you with less than $1 kind of prices.
Yeah, thank you, Mr. Anup, for the valuable information about isolation on the devices. So, yeah, I think most of the things you have already answered, and in the session also it was very much informative, and you have given a lot of information today. And I request participants, if you have any more questions, you can type on the chat box, or else like you can also type the questions on our forum, the people who are continuously participating in our sessions, and also I would like to announce about our next session. We are going to conduct the technical session on next Sunday. So just I'll show you the screen.
Have you seen this?
Ashraful, it's supposed to be Saturday.
29 August. Oh yeah, it is on Saturday, correct. Yeah. So it is session 8.3. Requesting everyone to mute yourself, please. Thank you. Yeah. So session 8.3. So this is the technical session we will be conducting on next Saturday, 29th August, and we will start from 11:30 to 1:30 this time. So instead of 11, we have made it 11:30. So you can also follow us on our YouTube channel. You can put the comments on the YouTube channel as a feedback, and also you can give some comments on our LinkedIn as well as on our Facebook. So which really helps us to improve our sessions for further for conducting further sessions and improving the quality of the sessions. So thank you very much for participating today, and special thanks to the panelists from Analog Devices, Mr. Sunil and Mr. Anup. And yeah, we will. Yes, sir.
Yeah. So can you move to the other slide, the rugger board one?
Yeah, sure, sir.
Say one thing. First of all, thank you very much to Mr. Sunil and Anup for a wonderful session, and I believe even our team from PHYTEC also captured a lot of information from this session, apart from our partners. So to the audience, what we want to tell is, on the rugged board, if you see the microbus connector, basically, so where it have all the interfaces, like UART, I2C, SPI, and then like you have interrupts. So we have couple of add-on modules which are developed using analog devices. So wherein which you want to quickly evaluate a couple of ADC, DAC, or any other IO IO interfaces, basically. So we can help you out. So we have off-the-shelf couple of devices, but we can also quickly develop and then help into your project in case you need a quick prototyping. So this is the reason why we have made the design of rugged board very modular. so that like easily peripherals or the sensor part, the analog front end, basically most of the time analog front ends are connected via SPI bus, so which is already part of microbus expansion connector. So that's the additional information we wanted to say. And then we have vast experience on Linux device drivers. We have developed a lot of ADC and DAG drivers on top of Linux from PHYTEC. So even analog team from India, analog devices, Indian team has been supporting a lot to our team in past couple of projects. Hopefully, any project related inquiries you can float to us, and then Arrow is a partner who can help you in the supply.
Thanks, Mr. Vasu. I think it'll be a good way to complement your core competence on these SAW modules with a software configurable I/O if the market demands it.
Yeah. So once again, thank you to all, keeping us motivated.
Yeah, thank you, Vasu sir. I thank everyone for participating today, especially for the analog device team and our participants on YouTube and MS Teams. So with this, I would like to conclude today's session, and we will see you on the next session on upcoming Saturday. You can visit our website www.phytecembedded.in, where you will get the meeting links. So thank you very much, and we will catch up in the next session. Bye bye.
Thank you.
Thank you.
Bye-bye.
Thank you. Bye bye.